Chemistry, we're on to our second lesson in Unit 7, Advanced Atomic Theory, and this takes a little bit deeper dive into electromagnetic waves. So the equations for the speed of an electromagnetic wave are given by this formula. There are several formulas, but the main one is this one, and it says that c, the speed of light, equals lambda, which is the wavelength. That's the Greek letter lambda. It looks like an upside down Y, times the frequency of the wave. Now the abbreviation for frequency, it looks like a V. It's actually the Greek letter nu, and it's often confused with the V for velocity that's sometimes used in class, but this is actually nu, which is frequency. So the speed of light is c. That's 2.998 times 10 to the 8th, or again, we oftentimes say 3 times 10 to the 8th meters per second. That's a constant, so c is not a variable. It's that very specific number right there. That funny looking upside down Y is wavelength. It's lambda, and it's the Greek letter. It's pronounced lambda. So wavelength is a distance measured in meters, nanometers, or some other unit of distance. And nu is the frequency. So nu is the Greek letter nu, pronounced nu. Frequency is the number of cycles per second and is measured in either hertz, seconds to the -1, or 1 over seconds. Those are the units of measure for frequency. So let's take an example. So speed of light equals the wavelength times the frequency. Now when you think about that, if the speed of light is a constant number, 3 times 10 to the 8th, then as the wavelength gets greater, that number becomes bigger, lambda becomes bigger, then the frequency has to become smaller by a proportional amount. So if you double the wavelength, you have to cut the frequency in half in order to make them both multiply to be the speed of light. So again, c is a constant number, the speed of light. So radio waves have the longest wavelengths and the lowest frequencies of all electromagnetic waves. So here is an example. So we say c is 3 times 10 to the 8th. Now we're going to say the wavelength on a radio wave is 3 meters, and that's pretty typical. It could be 3 meters, it could be a mile. Radio waves have very long wavelengths. And we're going to say that therefore that the frequency would have to be 100 million hertz, or cycles per second. So the 3 and the 100 million have to multiply to be 3 times 10 to the 8th, which is 300 million. Gamma rays have the shortest wavelengths and the highest frequencies of all electromagnetic waves. So there you see, again, c has to be 3 times 10 to the 8th. That's the speed of light. It's a constant number. There you see the wavelength is very short. It's 3 times 10 to the -11th meters. And therefore the frequency has to be very large. It's 1 times 10 to the 19th. But the frequency times the wavelength have to multiply to equal 3 times 10 to the 8th. In all cases, the wavelength times the frequency of an electromagnetic wave will be equal to the speed of light. Now, light also has characteristics of an object, like something with mass almost. And these objects are called quanta. And quanta are packets of light called photons. Think of a photon as a little ball of light energy rather than a wave. A photon has a definite amount of energy based on the frequency and wavelength of the light. Light can be treated both as a wave, which we talked about in the last lesson, or as a particle, but not both at the same time. Don't totally try to wrap your head around that concept. Don't try to reconcile, well, it's a wave, but it's really a particle. Maybe the particle is just a little piece of the wave. It doesn't work that way. You just have to understand that in some contexts, it can be treated as a wave, that roller coaster type of wave that we talked about in the last lesson, or as a little ball, just like a particle of light. But there is an equation, a couple of equations, in fact, that tie the two together, the wave characteristic of light and the particle characteristic of light. So anyway, this relationship between the wave nature of light and the particle nature of light is called the wave-particle duality of light. Duality means two things. Wave-particle duality of light. So there's the wave, or there's the particle. And it's treated as one or the other, but not both at the same time. Okay, so here are some formulas of electromagnetic waves. We're only going to deal with the top three in this class. So you already saw number one. Now we're at number two. Now what this means is that the energy in a photon is equal to a number, a constant called Planck's constant, times the frequency. So the frequency is a characteristic, is part of the wave characteristic of light. A wave has a frequency to it. We talked about that in the first lesson. The energy is the energy in one of these little packets called a photon. So you can see that this equation relates the wave nature of light, which is frequency, to the particle nature of light, which is the energy of one photon. So it's E of a photon, energy of a photon equals Planck's constant, which is h, times the frequency, which is nu, h times nu. So let's read this. So Planck's equation relates frequency, the part of the wave nature of light, and energy of a photon, part of the particle nature of light. A photon is a particle of light. Think of it as a little ball of energy. E represents the energy in one photon. Frequency is a characteristic of the wave nature of light. H is called Planck's constant, and there it is. It's a very tiny number, 6.626 times 10 to the negative 34th, and the units are joules times seconds. So H is called Planck's constant. Now you see a third equation, and if you look at the third equation carefully, you can derive it from the first two. You have C equals lambda nu, that's equation 1. Equation 2 is E equals Planck's constant times nu. So if you do a little algebraic rearrangement, and we'll just do this in class one time, you don't have to do it regularly, then you have energy equals Planck's constant times the speed of light over the wavelength. So what the equation 2 does, we know that frequency is a characteristic of the wave nature of light, so it relates frequency to the energy of a photon. Number 3 relates the wavelength, which is also a characteristic of the wave nature of light. So it relates the wavelength, that's the lambda down on the bottom, with the energy of a photon. So if you know either the frequency or the wavelength, then you can know what the energy in one photon is. So this version of Planck's equation relates the wavelength to the energy of a photon. This equation is formed by C, speed of light, equals lambda times nu, and E, energy of a photon, equals Planck's constant times nu. And if you do a little algebra on those two equations, you end up with equation 3. Again, H is Planck's constant, 6.626 times 10 to the negative 34th joule seconds, and that is Planck's constant. Equations 2 and 3 relate the particle and wave nature of light. So that's the significance of those two equations. So physicist Max Planck developed the equation for the amount of energy in a photon. Energy has the unit of measure of joules. Joules is the unit for all types of energy. The Planck-Einstein equation relates the energy in one photon to the frequency of the light wave. So we saw this in the last slide. So we added the subscript there, photon. The energy in one photon is equal to Planck's constant times nu, which is the frequency of the wave. Combining equations 1 and 2, we get, from the previous slide, we get the energy of a photon equals Planck's constant times the speed of light over lambda, the wavelength. So you have a way of relating the energy of a photon either to the frequency or to the wavelength. Depending on which one you're working with, you can use either one of these equations. So H is Planck's constant, V is the frequency measured in hertz, lambda is the wavelength in meters, m, and c is the speed of light, 3 times 10 to the 8th meters per second. Now, where do electromagnetic waves come from? This is an interesting little topic here. When an electron falls from a higher orbital, which is an energy level, it releases energy in the form of an electromagnetic wave. So there you see an electron that was on the 5th orbital and it fell down to the 2nd orbital. So when an electron falls to a lower energy level, an electromagnetic wave is released. So I'll show you that one more time. There it is on the 5th, and now it falls down. Now, why it falls down is beyond our concern, but they do. They move between energy levels, electrons do. So we're going to say this one just fell down from the 5th to the 2nd. An electron can be promoted to a higher energy level or even be released from the atom by an incoming wave. The release of an electron would be ionization. You know that as ionization, releasing an electron, pulling an electron away from its atom. So the Balmer series. In hydrogen atoms, light is produced according to the Balmer series. The Balmer series represents wavelengths of electromagnetic waves that are released when electrons fall to the 2nd energy level or orbital. So we're going to see the different colors of light that you will get from hydrogen based on which orbital the electron fell from on down to the 2nd orbital. So specifically for visible light to be produced, they have to fall to the 2nd orbital. These waves produce electromagnetic waves in the visible light range. The wavelengths released are as follows. So if it falls from the 6th orbital down to the 2nd orbital, it's going to release a wavelength that is 410 nanometers. That's 410 times 10 to the minus 9th meters. And that's going to produce violet light. If it falls from the 5th orbital down to the 2nd, so that's going to be less of an energy release. Okay, that's going to be a wavelength that's a little bit longer. The frequency is a little bit shorter. That's going to be a wavelength of 434 times 10 to the minus 9th meters, or nanometers. That's going to produce blue light. If it falls from the 4th down to the 2nd orbital, notice that as we go along, it's not falling as far, and therefore it's not releasing as much energy as the 6th orbital, for example. So 4th down to 2nd is green light. So that's a lower energy type of light. And finally, if it falls from the 3rd down to the 2nd orbital, that's going to produce red light, and that's the lowest energy. So the further the electron falls, the more energy is in that light. That means violet light is the highest energy, red light is the lowest energy because it fell the shortest distance. Now there's two other series. They're not quite as interesting because they don't produce visible light, but they do produce electromagnetic waves. Those are the Lyman and Paschen series. So the Lyman series is similar to the Balmer series, except it measures wavelengths released by electrons falling to the 1st orbital. And there you can see it over there on the left side of that image. You can see that the electrons are falling from the 2nd, 3rd, 4th, and 5th down to the 1st orbital. And they're going to release various wavelengths of light, but it's not light that we can see because it doesn't stimulate our eye in just the right way for it to send signals to our brain saying, hey, there's light there, there's color there. So these could be hitting your eye, but they won't stimulate the nerves in your eye, so you don't see any visible light. So there's the Lyman series. It's the one furthest on the left there. You can see the Balmer series in the middle that has the 4 colors that we just showed you, and that's falling down to the 2nd orbital. And then falling down to the 3rd orbital is the Paschen series. So the Paschen series is similar to the Balmer series, except it measures wavelengths released by electrons falling to the 3rd energy level or orbital. So remember, the one that's visible light is called the Balmer series, and those are electrons falling down to the 2nd orbital. You don't have to understand it any deeper than that at this point. Just understand that concept. The numbers on the graph are the amount of energy required to release an electron from an atom. Remember, this is called the ionization energy of an electron. So if you look at the 2nd orbital where the electrons are falling down in the Balmer series, that's negative 3.401, and those are called electron volts, and that's another unit of energy that we won't speak of that much in terms of what it is. Just to understand it's a measure of energy. So it would require positive 3.401 electron volts to release an electron from the 2nd orbital. You can think of that as the ionization energy. Again, usually we talk in terms of joules, but electron volts is another measure of energy. The numbers are negative because positive energy entering the atom would be required to ionize the atom. So we know that energy in is always a positive number. You put energy into an atom, that energy will then pull the electron out if it's enough to meet its ionization energy. So negative 3.401 electron volts is the ionization energy for an electron in the second orbital of a hydrogen atom. Now, the electromagnetic spectrum, what that is it's simply a picture of all of the different wavelengths of light, and or a graph rather, of all of the different wavelengths of light. So the wavelengths of electromagnetic waves range from over 1 mile, that would be for radio waves way over on the right side of that diagram, to 10 to the minus 12th meters, which would be way over on the left side where gamma rays are. Since wavelength times frequency of an electromagnetic wave must equal 3 times 10 to the 8th meters per second, wavelength and frequency are inversely related, meaning as one of them goes up, the other goes down. The energy of an electromagnetic wave is determined by its frequency, not its amplitude. That's a little bit surprising. It was to me when I studied this, and it's surprising to many students. You'd think that the height of the wave is how much energy it has, but it's not. It's its frequency that determines how much energy an electromagnetic wave has. The range of electromagnetic wave frequencies and wavelengths is called the electromagnetic spectrum. And that's what you're seeing here. So let's look at this. Way over on the right are the longest wavelength, highest frequency, so longest wavelength, smallest frequency number, lowest frequency, I should say, and they are also the lowest energy. Look at the very top of that diagram. You see increasing energy goes from right over to the left side. So radio waves are have the longest wavelength and the lowest frequency. So they have the lowest energy because they have the lowest frequency. Next you have infrared. That's the waves that carry heat. And those are a little bit more energy, a little bit higher energy than radio waves. There is actually another class in between those two, radio waves and infrared, that you've heard of. It's called microwaves. That's in between those two. Next, when you go over from infrared to the left, you see there's this little tiny sliver. It's so small they had to break it out down below. That's the visible light spectrum. So of all of the types of electromagnetic waves, only those in that little sliver between where it says ultraviolet and infrared, that's visible light. Those are the ones that can actually, they're at exactly the right frequency to stimulate the nerves in your eye to send signals to your brain that you're seeing light or color of some sort. So they break it down below. So if you see over on the right, again, the right side of this diagram is lower energy. So red light has the lowest energy of visible light. Way over on the left is violet light. That has the highest energy of visible light. And you can see how they go from right to left, from lowest to highest energy in that little sliver. Next to the right is ultraviolet light. Ultra means above, so it means above violet light in terms of energy. Next beyond that, to the left, is X-rays. And finally, the highest energy, that would be the highest frequency, shortest wavelength, would be gamma rays. Now down below, you notice that light is often measured in nanometers. That's 10 to the minus 9th meters. And they like to make that a standard measure of 10 to the minus 9th meters. So you notice how you have them in hundreds. The coefficient is in hundreds, 400, 500, 600, 700. So this is one time when scientific notation, you don't try to make the number between 1 and 9.999. Remember how we said that when we were learning scientific notation? So for visible light, it's always going to be some number in the 350 roughly to 750 range, and then it's 10 to the minus 9th meters, which is a nanometer, nm. So the part of the electromagnetic spectrum that can be seen by the human eye is called the visible light spectrum, and this is very small. The order of the colors spells the name Roy G. Biv backwards. So if you start over on the right, you got red, orange, yellow, green, blue, indigo, which is somewhere between blue and violet, and then violet. So it's Roy G. Biv. That's just any chemistry book you ever pick up will have Roy G. Biv in it for the order. You just have to spell it in reverse. So there you see Roy G. Biv up above each of those. So violet light has the highest frequency, highest energy, and shortest wavelength. Okay, remember wavelength and frequency are inversely related, so high frequency means short wavelength. Red light has the lowest frequency, lowest energy, and longest wavelength. So again, the energy in light or in any electromagnetic wave is not a function of its amplitude, how tall it is. It's not like an ocean wave where you would think that a really big ocean wave, because it's big, because it has high amplitude, is going to have the most energy. It's not like that at all, and that's the concept you have to kind of understand. It's the one with the highest frequency that has the highest energy. According to Planck's law equation, energy equals h times v. The energy of the wave is determined by the wave frequency or wavelength, not by the amplitude. So higher frequency is higher energy, shorter wavelength is higher energy. So if you look at this is called a line spectrum, and this is the line spectrum for hydrogen and helium. A line spectrum is kind of like a fingerprint of an element. So any hydrogen atom is going to put out those four colors that we saw a few slides back. Red, blue, there should be a green in there. It doesn't look very green. And then there's the violet. Okay, so that's hydrogen. Helium has a different line spectrum. It puts out different colors like that. This is how astronomers can tell what elements are in stars that are many, many billions of miles or many, many light years away from us, is by this line spectrum. They can break down the light coming from a star and see what the line spectrum looks like, and they'll know whether it has hydrogen or helium or what other elements it has in it. So this is kind of a neat concept for studying the stars. So let's take an example. What is the wavelength of an electromagnetic wave with a frequency of 4.28 times 10 to the 14th hertz? Express your answer in nanometers. And what is the color of that light? So light is an electromagnetic wave, therefore it has a speed of 3 times 10 to the 8th meters per second. Use the formula and solving for the wavelength, we get C equals lambda times V. Now it's asking for what is the wavelength, so we need to solve for lambda. So we do a little algebra there. We just divide both sides by nu. And I called it V. It's nu. It's frequency. So lambda equals C over nu. Okay, now you can plug in the numbers. You have the speed of light on top, 3 times 10 to the 8th. You have the frequency of this particular wave, which is 4.28 times 10 to the 14th. When you divide those numbers, you cancel your units. Numerator bottom, denominator bottom, and you get meters for your final units, and you get 7 times 10 to the minus 7th meters. But it says express it in nanometers because that's the way we always express light waves. So the wavelength of light waves is always expressed in nanometers, so 1 nanometer equals 10 to the minus 9th meters. So there it is, that's what we came up with for our answer. Now we multiply that by 1 nanometer over 10 to the minus 9th meters. We see that meters is going to cancel, and nanometers is going to end up in our final answer, and we end up with 7 times 10 to the 2, which is 700 nanometers. And wavelengths of light are always expressed in some number of hundreds of nanometers. So in this case, it's 700 nanometers. There it is, 700 nanometers. Based on the electromagnetic spectrum, a wavelength of 700 nanometers produces red light. So we know that we have red light there. And that takes care of this lesson on electromagnetic waves. You'll get some problems to practice on this and practice. There are some number problems, and I will put up an answer videos on this at a later time.